Okay, so I'm really happy to be here today in a room full of packed with a full knowledge from both sides, front end and back end. But the real fact about full stack is that everyone has a strong side. Can be persistent, can be microservices. My strong side is front end. And I believe everyone who is strong side is front end know that scary moment. So you start a new job or join a new team, and then someone point at you and say, this guy is good at CSS. And from that scary moment, you don't have lunch at 1 p.m. like you does. You just help your team with the CSS lag. Now, let me tell you about even scariest moment is that when someone point at you and say, this guy is good in UI performance. And I'm Gabriel, and someone point at me and say that. I wasn't good, but today I want to share with you the quest I developed how to be better in debugging UI performance. So short about myself, I'm like 10 years in full stack development, and again, mostly in front end. Now I'm a tech lead at JIT, a startup that's trying to break the friction between security and developers without letting developers love security. We do all the work. My story with UI performance started in early 2021. I joined Palo Alto Network to work in a product that has exponential growth. That's a cybersecurity product that grows from 0 to 100 million ARR in like 5 years. And the same as the business grows, the product grows. There was many features of the product that no one knows because we developed them back then to give to a customer. But then someone find them and trying to use them. And 1 month after I joined, I first got this bug. Now, it was only the first in a series. Every week we got the same fashion of a bug. Maybe you know that's a window or a snapshot of a snap. And the customer always say a very short description how it's happened. So something like, I entered to incident page and the browser crashed. I scrolled the table and the browser crashed. And when you got the screen, you don't really know how to start to act with that. So the good thing about such bugs is that you can always say it's unreproducible, closing the bug and waiting for a call from the customer. And 50% is work. You really get free. But in the other 50, they call you in a Zoom call, but at least you have some instructions on how to do that. And when you have these instructions, at least you can do something to understand it in your environment. We'll talk about environment later. It's not so simple, but we're here for that 50 part. Now, we are not here today for like performance that happened from a large size of JavaScript files, etc. That's not my point today. My point is about real performance issue in progressive web apps. And when you get those bugs, it's time for science of deduction. Now we're in London, and I love detective stories, and I know that I should choose Sherlock Holmes. But I love to engage my users, and I made a Twitter poll, and my guys choose someone else. If you want to affect, you can just follow me and affect the next time. So let's welcome the most famous Brooklyn detective that we ever knew, Jake Peralta, that will help us today. I know he's a bad detective, but I love him. He will guide us on a tool. The tool that we're going to use today is a Chrome Developer Tools. It should work in any kind of developer tools like Firefox and Microsoft Edge, but I love Chrome, and I hope you do. And I'm using Chrome. And the quest of having a debug of performance issues is going from console to network to memory to performance. If you know the developer tools tabs, that's the tab that we'll use today. And this will be the quest for us to solve performance issues. So what is the first thing we remember is that Peralta investigate murders. So he got into the room and started. That happened moment after moment after moment. 4 hours ago, if we look at his notebooks, we see 1 line. I have no idea how that happened. And when we have that, we need a tool that will help us to understand how things happen, how the bad things happen. So the first one is environment. Sometimes the customers use very different environment that we are using. So, for example, in Palo Alto Networks, we have customers that work in RDP consoles with 500 megabyte RAM. And when I'm trying to reproduce something in my 32 giga M1 MacBook, it will never happen. So we need to find a way to throttle our environment. So the DevTools has that button you can see, which is blue, the mobile throttling. And if we click on it, there is a new thing in the top right. You can see we can throttle also hardware. It will affect the performance and the network tabs. We can throttle the CPU to be 4x slowdown, 16x slowdown. And we can throttle the network. And that's really helpful when we are trying to simulate or emulate the customer environment where we fail. The second thing is about going to the console. So if we look here, we see the script that the customer tell us about. We can see that the customer, there is numbers. Each number represents a tab that we can see harm profile about, etc. And the customer just click on them, and we trying to understand is like in a gap of 350 milliseconds, and we're just trying to reproduce it, but programmatically. So we can, after create a test, or just do it without clicking all the tabs again. But that's not happened in our computer, and we need to find a way how to reproduce it better, and this is how the console came us to help. So I can start playing. I'm start playing with the numbers, playing with the gaps. So for example, in my computer, I need more gaps. Maybe it's because the network is slower. I don't know why, but actually, after some investigation, I found that I don't reproduce it with the customer script, and even the customer is not reproducing it consistently, but with my script, I can reproduce it. So from this time on, I have a script that I can just use, reproduce the bug, debug it in the other debug tools, but as a critical moment for me to continue investigate the case. The console is actually a Swiss army of tools. I'll mention some more that helping for performance debugging. The first one, if you may know, is console time. You can measure time. So if you write some function, you can just log the time that happened for everything to help. You can also style some stuff. So if you have complex data to display, you can console tables into the console. You can also color stuff. If you ever open the developer tools at Facebook, you'll see a hiring message, which is very colorful and a lot of emojis and stuff like that. But I like the table because that really helped me to understand a large and complex JSON that may be damaged. And the last but not the least is console trace. So if I'm in a function, I can print the trace that I'm having now. So I have here a function that calls many detective names, and I can see the whole stack in the last function that does the pointing there, that does the console trace. Okay, so you have the full list. You can find it in the MDN documentation website. And now that we know how to reproduce our bug consistently, let's continue to the next thing. So first, let's check the stranger thing, pun intended. And what are the stranger things? So we know our application is supposed to work as expected. We tested that. We even have a performance test. We do it nightly or in our CI/CD. So maybe something happened out of our application. And in front-end application, out of our application is what came back from the server, came back from the internet, from the network. Is not only must be our server. It can be sometime some ads server, some analytics, things like WalkMe. Can be anything that came out of the browser. So how can we check? So when we handling external data issues, we can split it into families. So here is a car crash. In the left one, I am the tree. I didn't do anything. The car came and broke me. And this is when the external data just came in and something was bad there. I have nothing to do in my application. I have something to do in the server or in the service that send me the data. And the second one is a bad contract. So when I'm getting data from some external service, I have contract with it. The contract is saying that, for example, I am should get some format of JSON, and I didn't get it, so I need to fix it. So let's see what happened here. I'm getting into this page, okay? And I want to see what happened outside. So I see here the network. Okay, let me take it bigger. Okay, let me try to refresh the page to get all the calls done. Sorry about the time. Okay, so I guess every one of you already know this network type in some manner. So sometimes you're just trying to see the JSONs, but it has some tricks to see how it's happening. So let's click on this page, and let's see our stuff. Soon the browser will crash, I can tell you that. But the first thing is how we getting the customer data. So if the customer has a bad data, how can we deal with that? So the answer is HAR. HAR is HTTP archive. It's like a JSON file that contains everything happened in our application. Now, the good thing about this JSON file is that if the customer has some sensitive data, he wants to filter it, he wants to mask, he can just open it in his editor and send that to you only after he does some manipulation, so it's safe to bring you back the data. Okay, so now we can see the page is not crashed. Okay, so now the page crashed, and we can look here and see that the call itself, something is really bad with the call. Okay, we didn't even see the response here. So how can we debug it? So one good thing about the network is that we can export it. Now when we copy it, we can even copy it outside of the browser, but I'll use the fetch, which is the standard JS call, okay, and go to the console, and now I can check what happened with this call. So I'll do the call, okay, and I'll print the result. Okay, so this is a, I don't know why I call it E, it should be R, but then I want to console it. Yeah, we have a small mistake here. And somehow that's not happened. What I missed. Okay, anyway, I can just do this stuff, and I'll tell you that if I'll run this script, I'll discover that this response containing 100 megabytes of data. Now, 100 megabytes not sounds full, but if you're trying to render 100 megabytes of data, that will be really hard to the browser to do that. So we did this one. We got the 3000 JSON, the big JSON, and now we're trying to understand what happened there. I mean, maybe we don't own the data. Maybe we don't understand why the data looks so big. So that's time for the small details. Okay, so here, I can tell you the secret. We can see that the content encoding is gzip. And somehow, this response zipped from 100 megabytes to 500 kilobytes. And after we're trying to discover this file, we can take it to Postman, we can take it to CURL to make some more manipulation on the response and understanding why is the external data such bad. And now, let's move to the bad logic. So we need to find the contract. So one good thing about the network is that we can see here, if you back to the network, the call stack. So for every call, we can see the call stack, and we can see now, this is the logic. This is where we call this network call. I can tell you that the bad logic was actually here. It's a bit down there, but because it's a React component, very small, you can understand. Usually, you can just travel the stack trace trying to understand where was the bad logic. But here, we don't limit the children, and we had like 10,000 children. And this is why it's happened. So we solved that by looking at the trace of the network. But usually, when you bundle JavaScript file, you don't really know how the code looks like. So the code in your application usually looks like in the top left corner. It's minified, it's bundled. You cannot do anything with it. So the first trick is just use the formatted button that you can see. You can find it in the small left corner here. that will formatted the data. And the second is about source map. Short about source map, when you bundling your JavaScript app, it can be web app or other tool, it created a file called source map. Source map is like the tokens of the real code in the bundled code. And it's like mapping between the minified code and the source maps. And for us, what we've done is for every CI/CD run, we keep aside the source maps. And when the customer came, we just take the version of the customer and putting the local source map when we're debugging. And then even if the customer record the HAR with the minified bundled application, we can see that in our local environment. So here is the bad boy. So next thing after the unusual fact become a memory. So I don't know if anyone remember Piamento, but Jake is working hard to remind him everything he forgot. So if we look at the memory, we have this memory tab. I'll go back to the application. I already recorded in advance, so I'll not do the recording now. I'll just explain what happened here. But here in the memory tabs, we have 3 options to record the memory, to get a picture on what happened in the memory in our application. The first one is heap snapshot. Heap snapshot will take a snapshot of what happened currently in your memory. So your application ran, crashed. You should catch it before it crashed, because after it crashed, the memory is cleaned. But sometimes you should catch it and you get a whole system on the objects in the memory. Now that's much harder when your files are minified, because you don't really understand the token, the names of the objects, etc. But yet, you can get a good picture of what happened there. One of the things that we'll see later is about retained and shallow memory, but we'll expand on it on the real demo. The second is time allocation. We can just click record and do things in our app. And then in the end, you see the blue line. So the blue line is the memory allocation that's not cleaned until we end the recording. That happened if we have a memory leak. We can see the occurrence of allocation, that the blue line are not cleaned, and then trying to investigate what is the memory that never cleaned. And the second one, the time allocation is a very time consuming because it has a lot of memory that it records. And if your application anyway got to spikes of memory, it will crash together with the browser. So use it carefully or for short stop. If you need to do allocation for a long time, you can use the allocation sampling, which take much less data, but yet you can run it even for 10 minutes or 20 minutes to understand what happened. It's very helpful for a rich UI application, less for business and enterprise application. Okay, so we record the memory, and now a nice thing about the memory tab is that we can compare. So I already prepared in advance 2 memory sampling. The first one is in my environment. In my environment, it's 78 megabytes. In customer environment, it reached 934 megabytes. And if we look here, we can see something interesting. So there is a shallow side and a retained side. What is the difference between them? So here, for example, we have the objects, but objects are related to each other. And the garbage collector, when it's trying to clean up object, is looking if it has reference for another object. So in our case, the objects are really small. I mean, it takes only 10% of the retained size. What is the retained size is something else, which are not the object that we can see here. That's something that makes us to think this is the glitch of the memory leak. So some objects which are very small here but live for a long term are taking objects which cost much more. And I think about the memory tab is that we can compare. Okay, so if I'm click here, I'm seeing the comparison, and now I can compare the 78 megabyte with mine. So I can see some deltas, and I can trying to understand what is the difference between my memory sampling and a customer memory sampling, and detect the memory leaks just in time. Okay, so here is the comparison. But how memory leaks happened in the browser? So there are, the first one which happens sometime is kind of your fault. You're doing extensive function that keep in state or do some stuff very complex, sometimes some recursive function make it hard for the browser to clean up memory, especially if you use non-anonymous function. But that's mostly not the case. The most case of the common pitfall of memory leaks in the browser is detached element. So what is detached element? Here is a very simple HTML file. As you can see, we have here 4 elements. Everything is represented very well in the browser. Very simple. Now let's say that we have also JavaScript code. Okay, in this JavaScript code, you should never write things like that. But we're creating a span with a content. And from some reason, we are referencing it on a Windows Store object. Now, the Windows Store is living for the whole time that our application will live. Okay? So what happened now? We get the new content. Okay, we got a new element on the DOM. Also, the HTML DOM tree got it too. And the browser sometime running garbage collector cleaning. Now, garbage collector cleaning in the browser is not something you can manage and you even cannot expect. So sometime the browser will clean the memory of rendering, sometimes the DOM tree, sometimes the JavaScript executor. Can be many reasons for cleaning memory. One of them is cleaning a rendering element that making everything in the JavaScript executor engine to be cleaned. But what happened here? We are removing this element. It's going out from the DOM tree, but remember, the Windows Store still referenced it. So when the browser trying to clear his memory, this element was not cleaned. Detached elements are very common in libraries like React and Angular, especially if you remember Angular 1, and that's heavy scrolling on tables. That was the most reason for that. So Angular does write the calculation of the DOMs. It doesn't have shadow DOM there. Sorry for the deep diving, I like front end. But they doesn't have a shadow DOM here, and it was very expensive from the perspective of detached element. Next chart will be the performance. So we do everything. We found that the memory spikes, or maybe not spikes. We're really angry now, and we are going to the best tab in the developer tools, the performance tab. Now, I like this tab, although it has too much data. I already prefer in advanced recorded performance because sometimes it's really hard to record that. Sometimes it just takes long. Sometimes your browser crashed in the middle. You should have some expertise on recording successfully those stuff. But actually, after you do that right, it just happens. So what we see here. So let's look at the top of the screen. Oops. That's strange. Okay, cool. Okay, so let's look at the top of the screen. We're seeing here the row where we can see the hardware. We can see the CPU, the network, what happened here. Below that, we can see the network. Okay, everything happened at the network. And then the most interesting part of the performance, the flame graph. We'll get back to it, just let's move. Here we can see some line chart of what happened from the object perspective and the behavior. And below there is tools that will help us to understand the flame chart. So let's start. We can see here that we have a spike in the memory, right? So we started in like 500 megabytes, which I have a small app. It's not supposed to take more than 10 megabytes. But we see spikes, and those spikes is not ever clean. So we can mark it only a small chunk of the timeline that we want to investigate. And as you can see, I get zoomed out to something. Now I can even go to specifically see what actually cleaned up my memory. If I click here, it's hard to see here, but there is a small window, and everything I'm seeing in the flame graph is actually what happened that make the memory to be cleaned up or to spike up. Okay, so let's back to see it in a biggest resolution. And a good point to start with when you're trying to investigate the flame graph is the network. And I'll explain why. So JavaScript and the browser is actually work in single process. It do a lot of stuff. It has the same priority mechanism like V8, like you may know from Node.js. We prioritize times, we prioritize I/O action, prioritize the code itself. The code is actually run synchronously, but with prioritization to make him asynchronously. When a network calls came, that's the real place you want to investigate, because then something entered into our application and our code is trying to do something. Now, usually, when you fired all calls, when you enter to the page, then you will have a big blocks of blocking processes. So here, for example, we can see that immediately after we back from the shifting, we call the server to get something, and then we get a very long call. And now Chrome is actually tell us here that we can see this rand triangle that tell us something wrong, something takes too long. If we look, we can see that this one takes 7 seconds, which is not fine to render a table in 7 seconds. And we can try to investigate. So first, we can see in the top is the task and the native JavaScript runners that will run. Here we see function call. We can see events. We can see many JavaScript native stuff that started our work. But then we will see a real function. So here is actually usually in the bottom, here is in the top, but in the bottom of the stack, you'll see some React or Angular or whatever library you use. But then you will be able to see some better inspection of what happened. And we can see that perform unit of work take time. And we want to try to understand what is actually take this long time. And we can see that cell, which is my component that's not supposed to take so long to be rendered. OK, cell supposed to be rendered in half of a millisecond, not in 94 milliseconds. And I see that I can see only one function happened here. Now that's not true because under the cell has some more function, like I'm rendering the cell and do some more stuff. And the flame graph is built in the way that really expensive function is very easy to detect. So now I can see the 2JS is the function that takes so long. 2JS is a function of immutable that's a very expensive function. OK, we even open it much more. We can see the time between the 2JS that happened for another functions to happen even. So we can see that relatively to other function, it took too long. And it's also a recursive function, so it takes a really long time. We can understand that something is really bad here. I can tell you that that was the biggest root cause for our bugs in Palo Alto Networks. We're starting with immutable because it's a good library, but then everyone do the lazy stuff to make it work fast, and that's make our application really slow. OK, so we understand now the flame graph. We can see here the lines, which represent another stuff. So we can look at the DOM nodes. If you remember in the memory, detached elements are represented now in DOM nodes. So if we trying to match the time between the JS heap, what happened in the memory, what stay, what not cleaned, we can compare it to what happened in these lines here. So we talk about the flame graph, and now the last, but not the least, today will be the last, pitfall in UI performance. Now, you may heard about it, that's the silent killer of UI application, and it's called layout thrashing. What is layout thrashing? So if you look at flame graphs of application, you will always see this purple rectangle. Some of them is also with the red triangle there. That means here happens something that related to the browser, not must be related to your code, that take a very long time and related to the layout rendering. Now, let's talk about the layout thrashing and how to avoid that. So how the browser works, we have render instructions. This is our code. This is our code that telling, render me a table with 1,000 rows. OK, but we are instruct many instructions to the browser. We can instruct him to display buttons and headers and navbar, etc. But we start with instruction, and then the browser take it into the JavaScript execution, execute the code, and then build the style. That's the first thing happened after we have HTML DOM nodes that we can render. The browser build the style. Then it build the layout, OK, the DOM tree of the layout. Then it compose everything to something it can render, and then natively, OK, it's not HTML anymore. It's just instructions for the C++ maybe or Rust engine that run the browser. OK, then you paint it, and that's queue, batch queue. It's happen again and again. So taking a batch of instructions, do their stuff, their native stuff, paint it, and do it again. Paint it and do it again. And the browser has a very smart algorithm how to manage it, how to make it synchronously, but do not stack your browser, etc. But what happened if sometime we instruct, so we tell the browser, render me a div. And then when the browser was in the middle of a layout step, we ask him what is the size of that div. So what the browser do, it will prioritize the queue with the current element, and then we'll get the bomb, because all the other elements, all the queue will be break. Now, if we look at this simple in one element, that will do nothing. But let's think about a table. Okay, so we have a React table with 1,000 rows, and if you know how it's happened with component today, every cell can be even 10 or 20, a tree in 20 levels nested component. And then if, for example, for each cell, we're asking what is the size of a span inside the cell while trying to render while the browser take the render of the whole table, something will take a long time. And longer because the tree could be really nested. So how to avoid layout thrashing? So usually if you got a layout thrashing, is a problem of the library that you run with. You can report a bug, but sometimes it's related to you. I can say, so one of our biggest layout thrashing in a level of like 1 minute to render a pretty small table was a bad table component that we write. The point is understanding when you read something from the DOM. So you can manage it in many ways. Sometimes you can use external canvas. Sometimes one of our pitfalls was that we use different ways to read something from the DOM. We didn't use React utilities sometimes. We're just trying to write our utilities ourselves. I don't know why, but that's happened. And that's make even the React mechanism to manage the layout thrashing to fail. So this is the last one that we talk about today. So we have kind of a lot to learn. And this quest is actually something that you can maybe remember, or it's too complex. So we starting with reproduction, do it consistently, and do it automatically. Then we look at the external data, what can happen out there in third-party services, in the server. Then we look how our contract work with this external data. Then we're trying to debug memory leaks, and the most memory leaks will be detached elements and untracked object, like a global object that being bigger and bigger. Then we look for extensive function that may be block logic. So again, for example, 2JS was a synchronic function. Nothing can happen in the time that 2JS is run. We look on that, and then the last thing to do is look at layout thrashing, which can be the reason for some of your UI performance issues. So thanks for listening. I'm really happy to share my story because that was my job security until I left for my will. But anyway, let's keep in touch. I'm on Twitter, not really on GitHub, but I have a profile there, on LinkedIn. Thank you.
Thank you very much, Gabriel. Do we have any questions?
We have a few questions from the online conference.
Great.
The first of them is, do you happen to use the dev tools in any other browser, such as Safari? Is there anything better they do than Chrome?
So I don't remember what it was, but sometimes Firefox performance of the dev tools was better than Chrome. Chrome is a memory consumption. Chrome has extensive memory consumption. And sometimes when your application memory spike to 8 GB, you will want a browser with less memory. So then you use Firefox. Again, I use Chrome, but Firefox works mostly the same. And this is actually a race. So every browser releasing their debugging tool, and then the other browser release that too. So sometimes you have something. So for example, now Edge has a very powerful tool to debug detached element, which doesn't come to the other, but I believe sometime Google and Firefox will do the same.
Thanks for that. We also have a question from Oscar Molnar, who asks, are there any extensions that you use that might help debugging? I know there's some good ones like the React DevTools, Redux DevTools. Do you recommend anything else?
Yeah, so that's fun because React DevTools and Redux are really great. But when your UI working slow or something, when the browser crashes, just make it crash more often. So I mean, when you do the small and simple performance debugging, the Redux and React are very helpful. I didn't want to combine them today because I didn't want to be platform or library specific. But when it became heavy, you should reduce all the unneeded extension. Another point that I forgot to mention is really good to debug performance on incognito mode. The way that Chrome manages memory is shared between the window, is managed between the tab. If you want to get a pure environment for your debugging, always use a separate incognito window.
Great tip.
Thank you.
Any other questions? Going once, going twice. Sold for Craig. Just joking.
Thank you.
Thank you, Gabriel. Our next session is at 2:20, so enjoy the little break in between.